So now, starting the next presentation, I think we have a recorded presentation now. The title is Row, Row, Row Your Boat, How to Not Find Weak Keys in Pilsung, by Chitchanok, Eyal, Ronen, Gregory, and Yuval Yarom. And we have a recording, so we'll just play it now. Alison, please, I think you have the recording, right? Yeah.
Hello everyone, I am Chitchanok Chuengsatiansup. In this presentation, I will talk about row, row, row your boat, how to not find weak keys in Pilsung. This is a joint work with Eyal, Ronen, Gregory, and Yuval, Yarom. First, let me briefly describe what Pilsung is. Pilsung is a block cipher. It is part of the North Korean Red Star operating system. Its construction is very much similar to AES, except that in Pilsung, it uses key-dependent permutation, which will be the main focus of our cryptanalysis. Pilsung follows a substitution permutation network design with multiple rounds to produce ciphertext. Subprocessors in each round are subbytes, shift rows, mixed columns, and add round key. Unlike AES, shift row in Pilsung is replaced by permutation, which is the main focus of this presentation. So next, let's take a look at how this shift row permutation works in Pilsung. This permutation basically shuffles a state which has 16 bytes, and it consists of several steps or several levels of shuffling. The first level of shuffling, it splits from 16 bytes into two groups of 8 bytes. And actually, at each step or each level of shuffling, it split into two groups of the same size. So now at the first level, two groups of 8 bytes. And at the second level of shuffling, it further split from 8 bytes into a group of 4 bytes. Or in total, we have 4 groups of 4 bytes. And at level 3, it further split from 4 into 2, or 8 groups of 2 bytes in total. And finally, at the last level, or level 4, we have 16 groups of 1 byte. And the result of shuffling or permutation is the concatenation of those 16 groups of 1 byte. And the important thing is how it determines which byte should go in which group. It uses some randomness to determine this. We will take a look into details of randomness used to determine which group it should go into. Again, at the first level of shuffling, it looks at the first 4 bytes and it uses 4 bits, one for each byte, and determine which group it should go into. If it is 0, then it goes to one group, the first group. If it is 1, then it goes to the second group, or the second half of the group. And to make sure that at each split, it results in 2 groups of the equal size. So within those 4 bits, there must be exactly 2 ones and 2 zeros. And then once it is done with the first 4 bytes, and it looks at the next 4 bytes. And again, it uses another 4 bits, having exactly 2 ones and 2 zeros. And split 2 bytes into one group and another 2 bytes into another group. And again, the next 4 bytes and the last 4 bytes. And if we look at the total number of permutation that can be produced by the first level of shuffling, we can see that uses 4 bits having 2 ones and 2 zeros. There are exactly 6 ways to represent this. And we have 4 sets of those. Therefore, in total, there are 6 to the power 4 total number of permutation produced from this level 1. And in level 2, it uses a slightly different method for the splitting or shuffling. This time, it looks at 2 consecutive bytes together, and then it either put the first byte into the first group, second byte to the second group, or it swap them around. First byte goes to the second group, and second bytes go to the first group, and so on. Which means that it uses only 1 bit to determine 2 bytes. And in total, there are 16 bytes, so it uses 8 bits, or the total of 2 to the power of 8 possible number of permutation produced at this level 2. And at level 3, it goes back and uses the same method as in level 1. Again, at this moment, we have a group of 4 bytes. It uses 4 bits. And each bit determines each of the bytes. If it is 0, it goes to one group. If it is 1, it goes to another group. And again, it must be exactly 2 ones and 2 zeros to guarantee that the group is equally split. Therefore, it has exactly the same number of possible permutation as in level 1, or 6 to the power of 4. Finally, at level 4, the last level of shuffling, it again uses similar approach as level 2. It looks at 2 consecutive bytes at the same time using 1 bit to determine whether swap them around or does not swap them. Therefore, at this level, there are again 2 to the power of 8 possible number of permutation. And if we put everything together, we can see that Pilsung produces 2 to the power of 36.7 possible permutation. And if we compare this to a random permutation of 16 byte, which is 16 factorial, it is 2 to the power of 44. So there's a gap between permutation that Pilsung produces and random permutation. And actually, with the random permutation itself, it may expose weakness when they do not mix the bytes enough. And we want to explore these weaknesses. In particular, we are interested in weaknesses that permutation preserve a column. And we will take a look what we mean by preserve a column. What we mean by preserve a column, we are looking at shift row that move all bytes in one column to another column, but again in a single column, as in the figure. So we move column 2 to column 4. Rows can be shuffled around, but again, it aligns in the same single column. And why is this interesting? If we have this, imagine that if we have this for the entire 10 rounds, we can easily distinguish between plaintext that produce from this permutation that preserve columns and a random permutation or ciphertext, or random ciphertext. Because with this, we can easily see that at the starting point and the ending point, we have exactly the same 4 columns. I mean, 1 column, 4 bytes in the same columns that are preserved. With this, we can build a distinguisher to distinguish between ciphertext that produce from Pilsung and a random ciphertext. And this is a simple way to express why we care about this column preserve shift row or permutation. And to build a distinguisher, we can reduce to actually looking at permutation that preserve round 2 to round 9. To take a look into more detail, so we start again with 2 plaintexts that differ at 1 byte. And in the first round, shift row will move that bytes around, and with the mixed column, it will propagate the differences to the entire column. And if it happens that that is a column that is preserved from round 2 to round 9, then by the end of round 9, we have 2 ciphertexts, or internal state of a ciphertext, that have exactly 1 column that is different, or 4 bytes different. And round 10, shift row will permute those 4 bytes around, and because there's no mixed column, then it remains that we have 2 ciphertexts that have exactly 4 bytes that are different. And in another case, it is the case that the differences is not in the column that is preserved. in this situation, we start quite the same way. So we are looking at two plaintexts that differ at 1 byte. And with the first round, shift row will move that byte around and mixed column will propagate the differences through the entire column. And if it happens that it is not the column that is preserved, which means that it preserves another columns that are already identical. So by the end of round 9, we have two ciphertexts that have 4 identical bytes. And again, with round 10, shift row will shift those 4 identical bytes around and there's no mixed column. It remains that we still have 4 identical bytes. So in either case, we ended up having two ciphertexts that have at least 4 identical bytes. And the possibility of two random ciphertexts that have 4 identical bytes is very small. Therefore, we can distinguish between a random permutation and the one that is created by Pilsung. And we can even push further this distinguisher and build a better distinguisher by reduce the requirement of resolving from round 2 to round 9 to round 3 to round 9. And to do so, we start with two plaintexts that differ at 4 different bytes. And at the first round, the first shift row happens to shift those 4 bytes into the same column, so they all align in one column. And mixed column happens to collapse those differences into 1 byte. So at this step, we have two internal states that different at 1 byte. And from round 2, shift row will move that bytes around and mixed column will propagate the differences to the entire column. And now we can consider shift row that preserved columns from round 3 to round 9. So by the end of round 9, we will have two ciphertexts that differ at 4 bytes. And because round 10, shift row will shift those 4 bytes around, no mixed column, differences remain at 4 different bytes. We can have this distinguisher of the requirement of preserving only from round 3 to round 9. So now that we know what we are looking for weak keys or keys that preserve columns, and we now need to see whether this weak key exists at all in Pilsung. Now we need to see, next we'll explain how we search for such weak key. So we develop an efficient algorithm to search for such weak keys. And first, let me recall about the round key. So one round key has 128 bits because this uses for shift row permutation, and we have 4 levels of shuffling. And we shuffle around 16 bytes, and each byte has 8 bits. So in total, 128 bits. And we start from round key 3 because we want to preserve from round 3 to round 9. With this, we select the first 64 bits at random, and we check whether this key can preserve a column or not. Recall that this part of the key corresponds to the first 2 levels of shuffling, and we want to make sure that the columns still align in the position that the columns still move to the position that they can still align in the same column. And once we have that, we proceed to select the second half, the remaining 64 bits of the round key 3. And once we have the entire round key 3, we can check whether this round key 3 indeed preserves a column or not. If it's preserved, then we continue to look at round key 4. We select the first 32 bits at random. And once we have in total 160 bits, we can now expand the entire round key. So we do so, we expand, and then we check whether this key can preserve to round 9 or not. If it can, then we say that we found a weak key. And then we increment this part, round key 4, the 32 bits that we select at random, we increment, and again we expand and we check whether it can preserve or it preserves until round key 9. We increment and we keep iterating this process until we say we should change round key 3. If we decided to change and we go back to step 1, we reselect the first 64 bit at random, and we check whether it can preserve a column. If yes, then we continue to select the second half 64 bit at random and check that indeed this entire round key 3 preserves a column. Continue to round key 4 and so on. Once we have the algorithm, we implemented this algorithm and we let it run on Phoenix high performance cluster at the University of Adelaide. We send a job, we let it run, and with this high performance, it can explore approximately 2 to the power of 25 keys per core per second. We spent quite some time, more than 10,000 CPU hours, and at the end of the run, we found multiple potential keys that preserve from round 3 to round 8. We could let it run further and to try to find the ones that preserve from round key to round 9, but we say we should at least check whether our algorithm works or not. So because we don't have it until round 9, so we need to modify the original Pilsung. So we modified it to reduce round Pilsung, specifically with 9 round Pilsung, and we test against this. And we found out that our attack actually fails. We tried to investigate what went wrong, and we noticed that there's a confusion between the representation. In Pilsung code, it uses 2 representations for internal state. But the first one is in the vector format for 16 bytes, and the other one is in the form of 2-dimensional array. And these 2 representations changing within the implementation. And we thought that from vector to 2-dimensional array, we thought that it uses row first order, or on the left-hand side of the figure. But in reality, Pilsung uses column first order on the right-hand side of the figure. What it means is that our algorithm actually searches for shift rows that preserve row rather than columns. So even though we have efficient algorithm, but the security impact of row preserve is questionable. Why is that? If we take a look at AES shift row actually preserves all rows. Once we have a more understanding of Pilsung, we again investigate whether it indeed can have permutation that preserve columns or not. Now I use same colors to represent the same columns because it is column first order. So the first 4 bytes is one column and the next 4 bytes is the next column. Again, if we look at the shuffling algorithm, the first level of shuffling splits into 2 halves of the same size, and it looks at 4 consecutive bytes, which means that it looks at 1 column at a time. And then it split 2 bytes into one group, another 2 bytes into another group, and again, there's no mixing across 2 different groups. And it then, once it's done with the first column, it looks at the next column, and again, it put 2 bytes of that columns into one group, another 2 bytes into another group. The same for the third columns and fourth columns. That is the first level. And in the second level, it looks at 2 consecutive bytes, which have to come from the same columns, and then it split them into 2 different groups. So it means that at this step, one column, a new column, each byte of the new column must come from each of the previous columns. So it takes one byte from one column, one byte from another column, one byte from another, and one from another, and put it into one column. And the last 2 levels of shuffling basically shuffle within those columns. What it means is that Pilsung shift row permutation actually ensures that no columns are preserved. To summarize, in this work, we analyzed Pilsung, an AES-like cipher with key-dependent shift row permutation. And we demonstrate how AES-like cipher with weak shift-row permutation can be attacked, specifically shift-row permutation that preserve columns. We also present techniques to efficiently search for such weak keys. We spent quite some resources to search for that. And we learned that we should highlight the benefit of early verification of the result. If we had tried to verify the result on, for example, one round preserve, we would have identified the error regarding confusion of the representation. Thank you very much for your attention.
Well, thank you, Video, for the good presentation. I see that Chitchanok is here to answer questions. Does anyone have any?
I have a question. Yeah, this is particularly fascinating to me now as a person who actually has to develop software in industry and think about all these tiny little things of representation. This seems like the kind of error that an implementer could make too, right? Like using the wrong representation and therefore creating a weak version of this cipher instead of a strong version. Do you think this might be a kind of inspiration for formulating a set of robustness criterion for cipher design that might protect you against misimplementation that leads to weak ciphers? Do you think there might be a sort of like lesson here in terms of that?
Yeah, so I think it's very, very good point. So that would be implementation error. So I think that would be like integrated into testing or maybe verification, because I mean, so there's like, it could be that there's not something wrong with the design, but then how the implementator implement it. So it would be nice to have some kind of like test factor into that. So if you implemented this, then you test against this, and then you check whether your implementation is correct or not.
Kevin.
Did you have a very precise description of the algorithm, or you were working from a reverse engineered description of the algorithm?
We worked on the reverse engineer of the implementation. So we have implementation, but it's not our implementation, it's the reverse engineer work of implementation.
And did you gain any insight from this study onto why they made this modification to AES in the first place?
Well, we believe that, well, they don't want to rely totally on like Western standard, for example, so they don't want to have their own standard. And probably they think by having key dependent, so it's create more like there's more like hidden data or something like that. So it could be more secure instead of having like non-dependency on the key. So this our thought, our belief that that's why they have their own key dependent permutation.
But it also seems like it introduces the possibility for weak keys too, in a way that doesn't.
Yes. That's why we investigate whether there's a possibility of the weak key, but with the weak key that we thought it doesn't exist, but it's possible that there could be different weak key, because if we look at the differences between the space of the random permutation and the permutation that Pilsung can produce, so there's some gap. So maybe there exists different type of weak keys, but within this work we did not find, with the preserved column we did not find that.
And I noticed you didn't mention the financial impact of this work like you have in your last paragraph.
Yes.
I believe that the standard question in cryptanalysis presentations is whether adding more rounds would make the cipher less vulnerable. So I'd like to ask whether removing few rounds would make it more vulnerable to your attack?
You mean reduce the number of rounds, like from 10 to fewer than 10 rounds?
Yeah, maybe to 1.
Yes, in that case, for the shift row permutation, there's no like preserved columns, but if it's reduced to 10 rounds, I would say the cryptanalysis would be somewhat similar. We have to take into account, like if we analyze AES, what would be security of reduced to 1 round or something like that.
Great. Then I'd like to thank Chitchanok and all the speakers of the session. And we have a 15 minutes break, so we meet again at 15 minutes.